Hello everyone, I'm Jiajun from Tianjin University. I'm really honored to represent all the authors to give this talk. This is a joint work of universities and the industrial corporation Microsoft. The title of our paper is How to Mitigate the Incident, an effective troubleshooting guide recommendation technique for online service systems. As we all know, that recently more and more traditional shrink-wrapped software is moving to online to provide continuous service. Those services cover every aspect in our lives, such as online working, cloud computing, communication, and so on. Online services are everywhere and have millions of end users around the world. Therefore, to provide stable usability of the service is an important task for vendors. But the fact is, online service usually encounter unexpected disruptions now and then. We call such unplanned disruptions incidents. They can affect the experience of end users. For example, when the user is working, the service suddenly cannot be accessed. It will be really annoying. However, the incidents are inevitable in real world because of software defects or uncontrolled factors such as power loss. In fact, the incidents not only affect the service availability, but may also cause great financial loss. This figure shows the cost per minute of an unplanned outage of data centers. As reported, the average cost per minute of an incident can be up to more than $8,000. As a result, it's critical to mitigate incidents as soon as possible. A typical incident mitigation process is when the monitors or end users report their incidents, the incident management system will call some engineers to mitigate them. However, the on-call engineers are changeable, and thus they may not know how to mitigate the coming incidents. At Microsoft, there is a good practice. Developers are required to record the mitigation process as TSG documents for known incidents, and then they can be reused to help engineers to ease the mitigation for similar incidents in the future. However, for some TSGs, engineers still need to query manually, which potentially could waste some mitigation time. Therefore, our question is it practical and useful to recommend TSGs for engineers? To answer this question, we conducted the first empirical study on 18 large-scale online service systems from Microsoft. In this study, we focus on the following research questions. The first one is, what is the ratio of TSG uses in online service systems? The second one is, what is the impact of TSG on incident mitigation time? And finally, what are the characteristics of TSG uses in practice? According to our dataset, TSGs are prevalently used by engineers. Particularly, about half studied incidents have associated TSGs. On average, engineers use TSGs for at least 27% incidents. Therefore, it's desirable to facilitate the uses of TSGs by automatically recommending them. Besides, after statistically analyzing, we found that TSGs can help shorten the incident mitigation time for 10 out of 11 services. And on average, the TSGs have achieved about 5 times speed up for mitigation. The result indicates that TSGs are effective to reduce mitigation time in practice. Finally, we analyzed the characteristics of the TSG uses. The result is engineers spend over 40% mitigation time on finding the desired TSGs for around 39% service. And engineers usually spend a significant portion of time on locating the desired TSGs. In addition, about 36% TSGs were repetitively used in our studied dataset. In summary, we can find that TSGs are exactly frequently used in practice, which help to reduce the mitigation time. However, engineers need to spend non-negligible time to find the desired TSGs. According to the above analysis, we conclude that it's useful and practical to recommend TSGs for engineers while learning from historical records. As a consequence, we proposed a TSG recommendation technique via leveraging deep learning approaches, which is called Deep Recommend. Generally, we used two neural networks to embed the TSG and the incident descriptions into semantic vectors, respectively, and then use the joint learning approaches to capture the semantic relation between TSG and the incidents for TSG ranking. The basic idea for our approach is incidents and their corresponding TSGs should be semantically similar. To embed the descriptions of incidents, we employed a bidirectional LSTM model with incorporating a attention mechanism to capture the key information. The reason is incident descriptions are usually not too long. However, as explained before, TSGs are typical documents that comprise multiple unstructured long tests. For example, it usually includes a short summary about the incidents it handles and the symptoms of the systems that the incidents produce, and many other aspects. In order to better capture the critical information, we employed text CNN model for TSG embedding, which was proved to be effective to handle long tests. Finally, we defined the following loss function as our optimization target, which describes the preference of the desired TSG against others for given incidents. Here, we use the cosine function to compute the similarity of semantic vectors. To evaluate the effectiveness of our approach, we implement as a TSG recommendation tool and perform experiments on it in large-scale online surveys from Microsoft. In total, there are more than 300 unique TSGs as recommendation candidates. We follow the chronological order of incident production to build our training and testing data. Besides, we compare our approach with two baselines. The first one is a traditional AR-based approach that uses TF-IDF algorithm for TSG recommendation, while the second one is DeepCS, which is adapted from a similar application scenario. We use the success rate as the measurement, which was commonly used in previous studies. Finally, here is the configuration of our approach in the experiment, such as the dropout value, the learning rate, the embedding size, and so on. This figure shows the experimental results for different approaches. Our approach is able to correctly predict more than 80% of TSGs at top 1, which significantly outperforms the baseline approaches. The improvements are about 47% and more than 100% respectively. The result indicates the effectiveness of our approach. Then we further systematically explored the effectiveness of different components in our model with multiple variants of our approach, such as removing the attention in the model, replacing the text CNN model with LSTM or vice versa. And also, we replace the cosine function with a one-layer full connected neural network to compute the similarity of incident and TSG descriptions. In total, we generated another 5 configurations of our approach for comparison. Here is the results. For simplicity, we only show the success rate at top 1. We can find that our approach is more effective compared with the other variants, where the improvements range from 12% to 190%. Importantly, though simple, the cosine function was really effective in our model. Finally, we further explore the impact of TSG description size to see the robustness of our approach. Lastly, our approach is generally insensitive to the size of TSG descriptions and thus has good robustness. According to our empirical analysis and experimental results, we also have learned some lessons that I want to share for future research. First, the current recommendation only provides the ranking result, lacking of sufficient interpretable information for engineers to decide whether the recommended TSG is correct or not. Second, since new incidents and TSGs will be added in the future, and old TSGs may also be updated along with the evolution of the system, online refine the recommendation model which will be helpful to improve the performance. We leave them as our future work. That's all. Thanks for your listen.